Okay, cool. Right, yeah, so I don't think he's doing this today. Right, yeah, because he's gone. Okay, so last week we talked about the Madeline equations. We talked about, let me maybe title it lecture 3. Local phase symmetry and electricity and magnetism. Okay, so last lecture we basically took the Schrodinger equation and we transformed it into the two Madelung equations, which remember transforms a first order in time, second order in space linear ordinary differential equation of the wave function into two coupled nonlinear differential equations, which consider not just the wave function, but its density, velocity field, and also, I guess, energy field, although that's maybe less included. In order to do this, we basically wrote this in its real and imaginary parts, and we defined here rho as the norm squared of the wave function, v as, before we used the first derivative, now I'm just going to move, because I want to do this in 3 dimensions now, so we're just going to make all the spatial derivatives into gradients.
So, was the energy epsilon required to get a complete description of the state, or did we just need rho and v?
You need, well, okay, so really what we have is, maybe, let me write these and then I'll write the equations and then that will help answer the question. Okay, so this is going to be h bar over m times the gradient of the phase field, and then the energy was defined as h bar, or minus h bar, times the partial of the phase field with respect to time. Sure, let's record it. Okay. And the equations that we wrote were the continuity equation, right? So, so it's a time derivative of the density plus, before we had a spatial derivative, but now it's going to be a divergence of the velocity of the probability current, which remember we could also write J as rho times V. So this is going to be the divergence of rho times V is equal to 0. And then the second Madelung equation was minus h bar, or was epsilon of x and t, but that's known, was equal to 1/2 mv squared, and now it's a vector, so that's like dot product squared, plus v plus q, where the quantum potential q, let's see, yeah, quantum potential q was defined as minus h bar squared over 2m times, before it was the second spatial derivative, so now it's going to be a Laplacian of the, well, let's say the norms of the wave function. You could also write that as square root of rho divided by norm psi. Okay, so now I'll answer your question, and then we'll pause for other questions. Yes, you do need the energy to fully describe all of this, because really what this is it's something that encodes rho, the probability density, and everything about the phase field, right? So this contains all of the information of rho and the phase field. If you just have v, then you only really encode the spatial dependence of the phase field. If you also want to care about the temporal dependence, then you do need this energy. So you do need all three of them. The reason why I'm sort of not emphasizing it as much is because in later parts of this course, we're not really going to focus on it as much, as it's a little bit more trivial, because often we'll be working in eigenstates, and the time dependence of an eigenstate is trivial because it's just e to the minus e n t, or h bar. Okay, so this is familiar to everyone? Any questions about this?
So it's the equivalent when we solve for the time independent and time dependent. We kind of solve for the time dependent one, and then we just know that we're going to attach that.
Right, for an eigenstate.
Yeah.
Right.
So it's just the same approach, basically.
Yeah. I don't know if any of you tried the homework, but for example, for an eigenstate, this thing is a constant.
Yeah.
So that's right. So that's why I'm sort of not emphasizing it as much, but
oh jeez.
But it's fine. Yeah. But for if you want to get more into the weeds of it, it will become important, and we can maybe talk about that when we get there. Okay, cool. Yeah. So now let's move on. Yeah.
Is it the case that classical effect and probability density, I guess density and velocity equation, we can derive the energy or energy equation?
Sorry, can you repeat the question?
Can, if we have a density and velocity field, can we derive or can we just figure out energy field classically? And then I guess my intuition is that if you know how much dense something is and how fast something is.
I see what you're saying. I mean, classically, also kind of quantum mechanically, right? Because you can say, like, the reason. Okay, maybe this is what Karim was asking. Maybe I answered it poorly. The reason why it's another thing is also, yeah, you could. Let's say. Yeah, given this and this, you have two known variables and one equation. So I think you could determine the energy, but it is like conceptually needed to fully describe everything. So yeah, I don't know.
I think
You could say it one or either way, but let's say yeah, knowing rho and v does determine them, but it's probably conceptually important to also say that it's different because of this equation.
like my question was very similar, but I think I was more thinking in the sense that like if you have psi without like the Madelung equation picture, right, and you're just like in the Schrodinger equation, that's all you need to know the state, right? Like you don't need to know like you can figure out energy just from psi, right? So I guess it was the same question in the sense like, yo, if I have rho and v, I have two equations that tell me the dynamics of that, right? Is the energy necessary to completely like pinpoint what the dynamics will be, or is that something that just kind of manifests within the dynamics?
The energy is certainly not everything you need for the dynamics. All of the dynamics is encoded in the phase. That's the point is that this, because it's a probability density, that is like at any given snapshot in time, just some like it's a thing. It's some scalar field. This, especially it's more clear in multiple dimensions, is a vector field. So it encodes both the velocity field of the fluid and also this sort of energy field, which could be determined from the velocity. But the velocity is the more intuitive one to think about because it's like saying how the fluid in an instant, in an infinitesimal instant of time later would move because that's what the velocity encodes. Yes, the wave function encodes all of this information, and it's just in this simple form. So often the Schrodinger equation is going to be a lot more simple because it's first of all it's linear and it also has this one thing. But remember, we did all of this, at least in last lecture, we did this to emphasize one, the fluid nature that you can write it in, and also to talk about the Galilean invariance issue that I introduced last lecture. Yeah. Keep asking, sorry.
Then, if you, for instance, have rho and energy field in 3 dimensions, we wouldn't be able to get V because velocity field. Is it correct? Because we technically have 5 unknown variables and 2 knowns.
What are your unknown variables? Sorry.
Velocity in x direction, velocity in y direction, velocity in z direction.
Okay, well, I'm saying you know all of those, right? Like that's what I mean by velocity.
What I meant to ask was, if we, for instance, have rho and probability density and energy, for instance, would we be able to figure out velocity field?
Oh, I see what you're saying. I mean, you'd be able to figure out, I think, the norm of the velocity field, right, from that. I don't know. I think, I guess let's say,
I mean, from the second equation alone, we should be able to figure out the norm.
right, but can you do this? Probably. I don't know if you have quite enough constraints. The reason why I'm hesitant about this is because the thing is that the energy, like you can imagine having different velocity fields that have the same energy at some given point.
Yeah.
Especially, or you could also imagine them being completely different and having the same sort of global energy if we were sort of integrate it all up. So I'm actually not 100% sure if you could do that. The reason why this is maybe, I don't know, this is a question that makes sense very much from the like fluid mechanics perspective, because you could ask that question in a fluid mechanics context. Also, I just posted the notes for this. Sorry. But I don't know. Here it's going to be. Here we're not really going to ask that question. We're mostly not, like, I'm not going to use this. The only time that I'm going to really ask you to use this as a very computational tool is in like the one homework that I gave. And that was again mostly for conceptual understanding. In order to utilize this in a computational way, like you're saying, given the energy field, there's some more stuff that you have to do that I'm probably not going to quite get into. Yeah, sorry, I don't actually. I'd probably have to think to give a confident answer. But yeah, I think not. Yeah, I can get back to you on that. Sorry. All right, cool. We can. Yeah, let's move on because I don't want to drag this on for too long. Okay, so we have all of these things, and then the thing that I mentioned was we said that there was an issue of Galilean symmetry in the Schrodinger equation. I was saying how, in order to see exactly how you transform the phase of the wave function, we wrote the equations like this, and then we defined our velocity and energy fields, and then that sort of allowed us to see exactly how one would transform the equation correctly in a Galilean manner. That symmetry, so let's say I'm going to move on to a second section called symmetries. The Galilean symmetry was what we would call a space-time symmetry. So it's a symmetry of the space and time that we live in. It's not the only space-time symmetry, right? It's in fact not quite the correct space-time symmetry. If we really wanted to be super accurate about this, we would consider Lorentz symmetry. By the way, has everyone here taken 103 or seen? Okay, you guys. Okay, just making sure that's important to know. Is anybody here familiar? Let's say, yeah. Is anybody here familiar with like 4-vector notation? Is that a? Okay, so that's really the main thing that I care about. I don't think it's taken 103, so it's fine. So the space-time symmetry, importantly, is one of, it's like a symmetry of reality, and it's a symmetry that we imposed onto the Schrodinger equation. So when I say imposed, I mean we had to do this, like, we had to say under a Galilean transformation, the velocity is going to change in a specific way, the energy is going to change in a specific way. The derivatives maybe is less clear, but specifically the energy, the velocity, and therefore the phase have to transform in a very specific way that we literally just say that they have to transform that way, and that allows these equations to have that symmetry. So it's a symmetry that is external from the Madelung equations or the Schrodinger equation itself that we then push onto the Schrodinger equation. And there's ways you can even argue that they fix the form of the Schrodinger equation, but even then it still requires you to do this sort of imposition. There are other types of symmetries though. I wonder, can anybody name another type of symmetry that the Schrodinger equation has? Where the symmetry is just something you can make some slight change, but it doesn't change the equations of motion or the probability density. Does anybody think of a particular symmetry?
Global phase?
Right, exactly. So global phase is what we would call an internal symmetry. So we'll say global phase. So global phase is, we send psi to e to the I alpha psi, where alpha right now is a constant. And then of course the norm of this is just unchanged. And then because this is a constant, In all of these equations, you can just factor it out. You know, rho, of course, doesn't change. And then v depends on the gradient of the phase, so the gradient kills the constant. Right? So in all of these equations, and equivalently in the Schrodinger equation, you know, if I write the Schrodinger equation, all of these, all of the phases can just be factored out and then they'll cancel. So this is the statement that you can rotate your reference of phase everywhere in space and that will not change anything. So this is what we would call an internal symmetry. So this is an internal symmetry because it's a symmetry of the theory itself. Like this symmetry, if you want a Schrodinger equation or you want these Madelung equations, you can't get away from it. It is there. And it's something that's built into the theory. It is, let me be precise so I don't say something misleading. It is a symmetry which, because it is built into the Schrodinger equation, that also means by this thing called Noether-Stan, which you may or may not have heard of, it actually implies a particular symmetry. So implies, and the particular, or sorry, not a symmetry, it implies a particular conservation law. So it actually implies conservation of probability. And Galilean symmetry on the Schrodinger equation, remember that was only for the free particle, also does this. Does anybody know what the implied conservation law for Galilean symmetry is?
Momentum.
Right, exactly. So this implies conserves momentum. And that's something that, this one I can actually get you to show on your homework without any 104 because you know Ehrenfest's theorem. This one is maybe a bit harder. After 115b you can do it. But both of these, because they are, I guess both of these imply conservation laws. This one implies a conservation law because it's a rule of reality, or it's an approximate rule of reality. This one implies conservation of probability because it's a built-in rule of the Schrodinger equation. We're going to now work with a slightly different type of symmetry, which is local phase symmetry. Or let's say local phase, I won't say symmetry yet, which says to send psi to e to the I alpha of, let's say, space, where it's a vector now, and time times psi. And this type of symmetry, or this type of transformation at least, does leave the norm unchanged, right? So this is equal to just the norm of psi. So rho is left unchanged. But of course, under this transformation, v and e are both going to change, right? So I can say that v is going to go to v plus h bar over m times the gradient of theta, gradient of alpha, and e is going to go to e minus h bar times the time derivative of alpha, right? So this is a type of transformation that very clearly changes our theory. And we're going to do something similar to Galilean symmetry, though it's maybe less motivated, where we're going to instead try to impose this symmetry onto our equations. So this is going to seem kind of unmotivated right now, but is that clear to everyone? You understand what we're trying to do here? We have various types of symmetries, and we're now going to introduce, and we're now going to consider a different type of transformation that we're going to make a symmetry. Cool, okay. Yeah.
Would it be appropriate to think of e to the I alpha term as a unitary time evolution?
So a unitary, it's a good idea. A unitary time evolution, which I'll say briefly because I don't know how many people are familiar with this. A unitary time evolution would be something like e to the minus I Hamiltonian t over h bar. So generally, you could imagine that this is, but it would have to somehow correspond to this alpha corresponding to h. There is No, actually, I don't want to say it. You can, there's like a context in which that could work out, because it could be that those just end up being the same thing. But generally, no, this is some arbitrary thing. If you remember, in the Galilean transformation, we had to do this, like, it was like theta plus mv naught x, minus mv naught x plus 1/2 mv naught squared t was what you had to change, you had to change the phase by. Here, we're just saying, ignore that specific phase transformation, we just want to do some general phase transformation on the wave function. And the reason why this is not a symmetry is because it's not a constant, and so these derivatives act on it. And importantly, it only changes the phase component, it doesn't change the density. Okay, so I'll sort of ignore that for now. We can talk about it later. It's maybe, yeah, I don't want to distract too much, because you could go down a rabbit hole with that. Okay, so as we said, this changes the velocity in the energy field. So what we're trying to do here is we're going to do the same thing with the Galilean symmetry, or a similar thing, and we're going to impose this symmetry onto our equations. For the Galilean symmetry, the reason we had a motivation for imposing it, which is that reality should work like that, right? In the non-relativistic limit. Reality, the equation of motion for a free particle should be invariant under a Galilean transformation. For local phase transformations, we don't actually have any physical motivation for this. There is maybe a way you can understand this. It is kind of like saying, so for global phase, this one is built into the theory, and it's like, basically global phase symmetry is, it's not a redundancy of reality, it's a redundancy of, I mean, it's not a symmetry of reality, it's a redundancy of the theory that we're using to describe it. Right? Like phase symmetries are going to literally be redundancies. So, and this is saying that for a global reference frame, you should be able to choose where sort of like your phase is pointing, or like your zero reference of phase. All this is saying is, you should be able to choose at every single point in space and time where your phase zero is. And that clearly changes the equation of motion, so you can't quite do that, but there's maybe a reason, like for example, this is unchanged, and you might just think, well, I kind of want that to be true. I feel like I should be able to choose a reference point for my zero phase at every point in space and time. And you can think that that's like because of like locality, for example. It's like, well, every point should only really depend on itself. Like it shouldn't, you should be able to choose it because of locality. I don't know. This is not something that I can actually motivate completely. The best way I can say is that we are actually going to change our theory in order to make this work out. And it turns out that that change will, of course, give us electricity and magnetism, which is very useful. So that's the actual motivation. It's that if you want to describe electricity and magnetism in quantum mechanics, you have to do this. Okay.
So in principle, with this local phase symmetry, I could always choose psi to be a completely real function.
Yes, that is something that is called, is it called the unitary gauge, I think? Or, wait, is that the unitary gauge? I think that's called the unitary gauge. We'll get into that in a second, but yes, you could do that. There are occasionally reasons to do that, and I don't think I can quite get into that in this course, although maybe during the last lecture we can talk about that. There's a lot of reasons to consider why you would do that. And that actually has to do with the question of these conservation laws. So yeah, we'll get to that. So that's correct. Okay, so in order to do this, let me make sure that I write the actual equations correctly. What we need to do is we basically tried to do similar to a Galilean transformation, but we're going backwards. We tried to change our energy and velocity fields without doing any change of our derivatives, right? Which is what it turned out that this change was compensated for by the derivatives, or really what we did was we changed the derivatives in the Galilean transformation, and then that was compensated for by a specific transformation. Here, we don't have the derivatives to compensate because we're not doing any type of transformation, any type of real, like physical transformation. So in order to compensate for this, we simply have to suppose that we have to redefine redefine our energy and velocity fields. And we're going to do that with this thing called the gauge field. So what we're going to say is that P, or sorry, let's say M, let me first do a preliminary, which is to say I'm going to define the momentum field as h bar gradient of theta. So what that means is that previously I could have written this as P squared over 2m, right? Because that's just the same thing. It's the same thing as redefining momentum in classical mechanics. I'm going to make that redefinition because it'll make this a little bit clearer. And what this then says is that I can redefine the energy and velocity fields in this new theory as m times v, which has units of momentum, so I'll include the m, is now defined as this velocity, right? Because before that would just be true, because you could just multiply v by m and get that. But now we're going to subtract off this thing q times a, where a is just some unknown thing, so unknown vector field. Similarly, we're going to redefine, this one is a little bit less useful, but I think it's good to include it, this new energy field as epsilon minus q times this var phi, or I guess just phi, I won't say the latex.
This might be a dumb question, but why isn't this a momentum density? Because it's like a field.
It is, okay, so they are momentum densities, I'm being vague when I say
Okay.
And it's also not quite a momentum density. We'll get, again, this will be useful in the lectures, but in order to call it a momentum density, we will actually need to multiply it by rho, because rho, where's rho? By rho, because rho encodes like how much of the wave function is there. It's like how much, it's a density field. So it's like the momentum density would actually be this quantity, which sort of gives you like a number, times the actual density of like the matter or whatever that's at that point. But yes, that's correct. These aren't total momentums or total fields, total quantities. They are varying fields in space and time, and that's important because the fluid is allowed to flow by rho. Okay. And we call these things. I think I still have, yeah. We call this thing, which I'll group into a maybe let's do this. I'll group into sort of brackets. I'll call it phi comma a, so it's like a 4 vector now, is what we call the gauge field. And this isn't the only gauge field, but for now it's the only one that we care about, so I'll just call it gauge field. We can make this more precise later. Okay, why can we do this? There's math reasons why this works. I don't think I want to talk about that right now. Just accept that this is something that we have to do in order to get this local phase symmetry. And what it is that these things are equipped with the transformation laws that under a local phase transformation, so an LPT, let's say the zeroth component of this thing, phi, goes to phi minus partial of lambda with respect to t, where this is some arbitrary scalar field that's related to our phase transformation alpha by lambda is defined as h bar alpha over q, where q is some parameter that we don't know what this is called now.
So does phi have anything to do with our like potential v plus q, or is it completely separate?
Ignore, yeah, so maybe for simplicity, I will drop v here. V is some external potential.
Yeah.
It has nothing to do with any of this.
Okay.
You can see that under a local phase transformation, these are unchanged because this depends on the norm and this is just like external.
Okay.
Okay, so these are like almost unimportant. Q is a little more important, but for now, V is unrelated to phi, although it will look like one at some point.
So just to get the picture of like what we're doing, I imagine phi is going to turn out to be the electric potential,
Right.
And this is a separate potential from v, right?
Right.
Because
So-
V is like an external one, and this one's kind of baked in after we make this symmetry, right?
Yes,
Okay.
you are correct. Yeah. So I mean, yeah, I don't really care about spoilers, right? This is of course going to be the electric potential. That's why I've named these things the way that I've named them. But yeah, this one, like, if you want local phase symmetry, you are forced to have a thing that looks like a potential, and you can also have another thing, but they are unrelated in the sense that, besides the fact that they both are potential energies, or in some sense, they, you can have change V however you want. It won't change V.
Okay. Yeah, didn't mean to spoil. But.
No. I mean, I think this is, if you've taken any amount of electromagnetism, this should look pretty familiar. If not, it's hopefully not too confusing. Okay, yeah, it's fine. And then the field A, can anybody, maybe if you've taken electromagnetism, guess how this should transform under a local phase transformation? So it should go A, and then, I don't know if you can guess it, yeah, Tom.
Is that the gradient of lambda?
Right, exactly. So it's going to go like plus gradient of lambda. And the reason why we choose them like this is because if you were to now check these, we define these in such a way such that these are invariant quantities. So I guess I could call these are our invariant momentum and energy, or velocity and energy, if you want to think about it like that. And then these are the gauge fields that we have to couple to them to our momentum and energy.
The reason that phi and A transform like that is because V and epsilon transform like that. So we're making a mapping between vectors and scalars. In the same ways,
Yeah, no, I mean, let me say that. I'll say that, like, make it clear in just a second. But let me just say the last thing is that because these are called the gauge fields, this is called a gauge transformation. Okay, so yeah, the reason why we define them like this is because we want these things to be invariant, right? That's the local phase transformation invariant. Because the whole point of redefining these was such that we wouldn't change the theory, wouldn't change anything when we do a local phase transformation. So if you check right now, right? So we can basically check that this works. So if we do MV under a local phase transformation or a gauge transformation, is going to go to P, right? But now P, because P is defined like this is going to get plus h bar gradient alpha. So this is P plus h bar gradient alpha. And then it's minus Q times A, but as we said, A gets plus gradient lambda. Right? Where lambda is the same thing as the h bar gradient alpha over Q. Okay? So these cancel, and then these two terms cancel, and then we just have P minus, or I guess Q shouldn't change. P minus QA, which is the same thing. So the point is that MV was previously equal to P minus QA. When we do this transformation, it remains P minus QA. Is that clear? So we defined these such that this would work out, and you can check the same thing for epsilon, that this will remain the same.
So I'm not seeing where the h bar gradient.
This is h bar gradient alpha. So the Q cancels with the Q.
Or I'm not talking about the second term. Where is that? Because we're taking P minus QA and we are transforming it.
So yeah, P transforms like this. Are you comfortable with that? Like P
No.
goes to P plus h bar about.
Top left.
Is that?
Yeah. Sorry. Okay. Let's. So here.
Oh,
Everything-
we're just saying, okay, no, I got it.
Everything below this line is new. Like these definitions are no longer, I guess, yeah, these definitions are no longer quite true. This one is, I guess, true, and then I redefined this. And then this one isn't true anymore because now it's defined like this. So
Yeah.
just don't use these definitions quite anymore. Use this definition, and then like, I guess also this one. Sorry, this, like I said, the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so the energy is kind of annoying because it like works, but the notation isn't super standard. Okay, so Okay, but sorry, yeah, you get this now.
Okay, so I would look, so when you say P defined as H bar, I mean, I don't see anywhere how we transform P. I can guess.
Oh, I
that
see what you're saying.
So we,
Well,
we
we
could
could just
multiply by
use
n.
the
Sure,
transformation of gradient theta, right?
So-
Because that's really what it's defined as. It's just h bar gradient theta.
so when you do e to the I alpha t,
Mhm.
theta becomes theta plus alpha, and p is equal to h bar times the gradient of the phase. It's not h bar gradient of theta before the transformation, it's just h bar gradient of like the phase field.
Mhm.
So it would be h bar times gradient of theta plus alpha, right? So h bar gradient theta is just p, and then you have an extra h bar gradient alpha.
Sure.
Sorry, you want me to write that out? And I can, if that's not clear,
Maybe if it doesn't keep.
Okay, yeah, no, that's fine.
Just
I want to erase this because I want space, but I'll write it first. So the point is that P is defined as like h bar times the gradient of the phase field. Right, so normally psi equals norm psi e to the I theta, right?
Mhm.
So all I'm saying now is under a local phase transformation, this would go to, because you multiply by e to the I alpha of x and t, this is going to go to norm psi times e to the I theta times e to the I alpha, right? But I can just write that as e to the I theta plus alpha. Right, so is that clear so far? Okay, so now I'm saying now p, right? Previously p was h bar gradient theta here. So p here, h bar gradient theta. But now this gets sent to h bar gradient theta plus h bar gradient alpha. So let's say, maybe let me get rid of the definition here.
Okay.
This is
I
p,
see
that's
what
p,
you're
and then we just
saying. I
add
see what
that.
you're saying.
Right. And then this is just, we just said that that has to be true.
Sure.
Right. So then these cancel. Yes.
So, let me just clarify. The reason we're checking that MV transforms in this way, or I guess that P transforms in this way, is to kind of, tell me if I'm wrong, is to kind of verify our choice for lambda, or
Yes, it's to verify really the choice for these transformations. I mean, I could call this anything and then define lambda. Yeah, it's to verify that this is a thing that is the correct way to transform these fields such that these are invariant.
okay.
Like really, the thing that we care about is that these are invariant. Because if these are invariant, these are the quantities that we care about. And if they are invariant, then our equations of motion are the same. They don't change. Right, so maybe I can leave that there. We'll do. Yeah, I'll leave that there. And hopefully you could do exactly the same idea for energy. It would just be the exact same thing. You plug in the transformation for epsilon, which is like this. Maybe I can include that here because that is actually important. So I would do the transformation for epsilon, and then I would do the transformation for phi, and those would cancel, and you would still remain epsilon minus q phi.
If I could just quickly summarize. So the idea is we want to impose this symmetry, and
Yes.
we noticed that in the current state or before we did all this, we had some things defined in such a way that when imposing the symmetry, we wouldn't get the same equations of motion. So now we're trying to redefine things in such a way that when we apply this symmetry, we do get the same equations of motion, and we have added terms and defined how they transform such that this is true.
Right, exactly. Yes. And
then now this is just verification.
yes, this was just because otherwise it would seem like why did I define
did
it
you
like
define
this?
it? Sure.
It's
Okay.
because that makes those invariant.
Sure.
Right, so that's, yeah, I mean, like you could have derived that, it's not that difficult, but I'll just say it because you're familiar with that form probably.
Okay.
You might have seen it before at least. Okay, any more questions on this? I'll move on to writing the new Madeline equations, if not. Cool, okay. So with that, we can rewrite these Madeline equations. This stays the same because V is invariant, right? I mean, it's MV, but M is a constant. So this thing is going to stay the same because rho is invariant under a local phase transformation. This one will change slightly. So I'll write the sort of what I'll call the gauge invariant. I guess I should say, a choice of this lambda function, or a choice of alpha, because they're related, a choice of this function is called a choice of gauge. So I'll say a choice of, like a choice of, in this language, a choice of phase, a choice of local phase is the same thing as a choice of gauge, because this is sort of just defines what the phase transformation is. So they're like the same thing. So I could say local phase invariant, but I'll for now say gauge invariant because that's a bit more standard language. Gauge invariant Madelung. And again, for now, we don't know what this quantity Q is, although of course Q is going to end up being the electric charge. For now, it's just some parameter that tells us sort of how strongly these fields are coupled to our actual equations. So if this was 0, then you would return to that thing, but as you turn it on, these things have more and more of a strong influence, you could say, on the actual variables that we set. Importantly, the reason why we wanted these to be invariant as well is because we, actually no, let's say because these are now invariant, these are the things that we care about, that we could actually calculate V, E, and also rho, but that's sort of trivial. Those things are the things that are, I guess I shouldn't say observable because they aren't, like V isn't always observable, but those are the things that could become observable. You could come up with a way to measure those, doing interference or something. These things, because you can do you can add, any arbitrary scalar function like this. I guess lambda is a function, it's a function of space and time. Those are, these are arbitrary up to this, redundancy. Like you couldn't possibly measure phi or a because you don't know what this lambda is, and if you let's say that you measured it, you could, without changing the measurement at all, change the value of these by adding some arbitrary scalar function, and then that would be a different value. So you can't possibly measure these things. The only things that you can measure are the things which are invariant. These things which are local phase invariant, or what we'll call gauge invariant. And we want our equations of motion to be gauge invariant because we want them to produce measurable results. So this is kind of a distinction of what we consider as real or not in our theory. And I say real, I basically mean observable, although that's technically more subtle. So this thing is going to remain unchanged. And then, and do people see why this remains unchanged? Is that clear to everyone? Okay, so this one is just the same thing because V is already invariant. Now I can rewrite this one, and I know I just defined this, but I kind of don't. I define this mostly as a formality. I want to actually explicitly show Q phi in this. So what I'm going to do is I'm going to write epsilon minus Q phi, or I'll write epsilon equals p squared over 2m. Now we need to modify the momentum by this, because really, remember, this was like 1/2 mv squared. So what we're going to do is we're going to plug into 1/2 mv squared using this formula. So this is now p minus qa quantity squared over 2m, and then plus v plus q. But because I have to subtract off q phi from this, I'm just going to move that to the other side and write this as plus q phi, and then plus v plus q. Where again, this thing is external. At basic, I could pretty much say that this is 0 for now. It doesn't really matter. It's completely arbitrary. This thing is a little more important because it depends on the wave function, so I won't say it's 0. But these are pretty much external from everything that we're talking about today, so don't really worry about them. Okay, so this, if you've taken 115b, might look pretty familiar. This is related to minimal coupling in E&M. We pretty much just did that. But these are now the equations that we want to work with. And we can derive certain things from them. Do I want to do it in that order, or? No, okay, I'll keep with the order in the lecture notes. So, okay, we've now successfully created a local phase symmetric or gauge invariant theory of quantum mechanics. But we had to introduce these things to do that. If we introduce these things, that means that they might have some life of their own, right? They could have some effect on reality. Clearly, they can't have a direct effect on reality because these things themselves aren't measurable, but maybe we can come up with some combination of them that is measurable. And in order to show that, I'm gonna use 4-vector notation for a little bit. I'm not, at least for now, I won't do any special relativity, but I am just gonna use the notation because it makes it a lot clearer what we're actually doing. Okay, any questions now? Cool. Okay, so I'm gonna I wrote this like this because I wanted it to kind of look like a 4-vector. We're gonna see, is it possible to create some combination of these that is gauge invariant, is really what we care about. So I'm gonna define, let's see, where do I put this? So I'm gonna define phi ax, ay, az. I'm gonna define these as a naught, a1, a2, a3. Okay. So this is literally just relabeling, right? And then similarly, I'm going to redefine. I'm going to label my derivatives as partial 0, or let's see, minus partial t, partial x, partial y, partial z is partial 0, partial 1, partial 2, partial 3. Okay. The reason why I define it like this is because now I can write the gauge transformation in this way. So I can write a sub mu, because now all of these are just labeled by some number. Under a local phase transformation or a gauge transformation, so I'll call it a gauge transform. Now, a gauge transformation is going to go to a mu plus partial mu times lambda, right? So now I can do this all in component form because of like this. Does everybody see why this works? It's because I define this minus, so now this minus is taken into account for, and so I can just write that. Is that okay? Is that clear, Leon? Are you all right? Are you good? Okay, cool. Were you good? Okay.
Can you define it differently here?
You good? Yeah. Okay, cool. Yeah, this is literally just labeling. Like, it's literally just labeling because I want to work with this, because otherwise I'd have to do a lot of math. I mean, that's just what representation is. It's a repetitive math. Is it 11 already? Okay. That's fine. That's why I made these longer. So, okay. With this form, we can now ask, what possible form could a gauge invariant form of A mu be? The first thing that, if you didn't know anything, you might be able to guess it here, but if you didn't know anything, you might guess that the gauge invariant form would be something that's like massive, where massive means it's like the wave function. Basically, the wave function has an energy penalty existence for like existing, because there is energy associated clearly in V and in Q and in the Schrodinger equation, right? You care. There is the fact that this costs energy to exist means in physics in a physics way means that it's a massive field. There's an energy cost for it to exist, and this is dependent on the square of this. So you might ask, is the quantity a mu gauge invariant? Is that notation familiar to everyone? If not, then I don't have to use it. I can just say squared. Yeah.
Does raising and lowering matter here?
No, it doesn't. But if people prefer, I can use the lower notation. It really doesn't matter. I mean, I can also say a mu squared. It's not a huge deal. The only point that I'm saying is that under a gauge transformation, that's going to go to a mu plus partial mu lambda quantity squared, and that is clearly not equal to that, right? There's going to be some cross terms that won't cancel. And you might say, well, wait, if this can't be gauge invariant, then what could possibly be gauge invariant? Because if a mu squared isn't gauge invariant, if a mu isn't gauge invariant, then any derivative of a mu isn't going to be gauge invariant. You could be like, well, okay, I'm never going to have anything that's gauge invariant, so it feels like this doesn't exist. The solution is there is one combination of derivatives that you can come up with, at least first order derivatives, that is gauge invariant. And that combination might look familiar again if you take A&M, which is to say, consider partial mu A sub mu minus partial mu A sub mu. Actually, you know what, let me rewrite that now. Am I writing this, is this large enough for people to see? I don't know if it's, okay, I'm just writing it smaller so I can fit. Okay. So this thing under a local phase transformation is going to go to partial mu of A mu plus partial mu mu, or partial mu lambda minus partial mu A mu plus partial mu lambda, which is equal to these two terms are just the same thing. Right? And then we have plus partial mu lambda minus partial mu lambda. Okay? Again, this is, yeah. That was a little bit of some algebra, so let me pause just to people follow the algebra. Pretty good. It's not that complicated, but the indices, especially if you work with them, can be confusing. Okay. So the point is now, the multivariable calculus rule says that the order of the derivatives doesn't matter. So these two terms are equivalent, and we can cancel them, and you see that we return to the same thing. So this is a combination of this is a gauge invariant combination of A mu, and it required us to take these first derivatives. And in relativistic notation, I'll say it here because this might tie some things together if you've seen this before. This quantity is what we call F mu nu. It's a 2 tensor, if that means things to you. And this is what will end up being called the electromagnetic field tensor. The reason why it is like this is because it's a gauge invariant combination of our gauge fields. So it's the thing that we could possibly measure, because it's gauge invariant. Now, there's a little tricky question that I guess I have time to briefly speak on, and that's that, well, okay, if this is real, then it's totally possible that you might be able to measure like higher powers of this, like you could measure like this squared or something. The thing is that all of those are really dependent on that. So that's really, this is the fundamental thing that we care about. Like if you did F mu nu, F mu nu. Okay, is that clear?
What do you mean dependent on higher powers?
I was like, you could like write like this squared or something. I'm saying like the fundamental quantity is F mu nu, but you could potentially measure like that.
Oh, that would also be invariant. Yeah.
Right. So there's other invariant quantities, but the things that we're going to care about here are F mu nu. There is technically a way to do higher order derivatives, but we're just not going to worry about those because those apparently just like don't exist. I don't actually think there's a good reason. I don't think there's a good justification for why they don't mathematically. I think it's just they just don't exist. But this one is the simplest one, and it's the one that we're gonna end up worrying about, and it's the one that will end up being familiar. Just quick show of hands: have people seen this thing before? Is that like you don't have to know what it is? Have you like seen that before? Ever? Yeah. Okay, that's good. It should like you like pop science or something. You'll see people talking about that. Okay. Now let's figure out what this thing is in maybe more familiar terms. Yeah, we have time. So that F mu nu, we can basically split up into zeroth components and so like components in the first row in the first column, and then just the spatial components. So I mean, maybe that doesn't make a whole bunch of sense, but firstly, you should notice that, of course, the diagonal components of this tensor are 0 because that would just be this minus itself. So we can just consider the components that don't have mu equals nu. So I'll write first partial, we'll just consider partial 0, partial 1. Do I want? Yeah, partial 0, A1 plus, minus partial A1, partial 1, A0. right? This thing is equal to, if we use our notation, can somebody read off what this is equal to me? Using this. Let me try. Yeah. So,
Minus partial of t of 5. Minus.
So I'll write this.
Minus the partial of x of 5.
Not quite 5, right? Because oh, I'm sorry. This is.
Oh, sorry.
No, you were right. Yeah, and then this is a1.
Sorry, A1.
X. Yeah.
Sorry.
So you're good. And then hopefully you can see that this is going to be. Actually, you know what? No, we'll do the whole thing. Partial 0 a2 minus partial 2 a0 equals the same thing, but just replace x with y. Partial 0 a3. And yeah, I know I'm literally just writing the same thing, but I think that it's kind of cool to see all of this work out. So we have partial az, partial t minus partial phi, partial z, right? And okay, these things you can kind of group into a vector almost, because you have x, y, z, and you can just say that this is equal to the time derivative, or minus the time derivative of a, and then this is just the gradient of a scalar field, so minus the gradient of phi, and then that, if you've seen any E&M, especially just looking at that, right, but then you learn that this is also important, we can define this as the electric field. Okay. So technically I'm just defining this as a thing that exists, but it should look familiar to you. At the very least, that should look familiar. And then if you take like higher level E&M, you'll see that that's also a term you have to add for time dependence. Yeah, so we did have to, this is a definition, it's not a, you know, it's not quite a derivation, but you can see the importance of E now is a gauge invariant manifestation of the gauge fields. And you could do exactly the same thing for the spatial components. And notice that all of these had time derivatives in them. I've used up all the partial zeros, right? I guess you could say if you swapped these, it's like an antisymmetric tensor. So if I swap these, then I had partial 1 a0, partial 0 a1. Then what I would get would be minus e. And that's just because, but that's dependent, like that's the same thing. It's just up to a minus sign. So it doesn't really matter. There's only 3 other components that we care about, and that's going to be the spatial components. I'll write one of them. So like, for example, partial 1 a2 minus partial 2 a1 is going to be equal to partial a y with respect to x minus partial ax with respect to y. And I think this is the curve, right? So this thing is the z component, right? This is the z component of the curl of the vector potential. And then if you were to do this for all the other ones, right, so you would sort of group these and you get the z, the x, and the y component, and you would define all of those, you would just define the curl of A as, let's say, equals curl of A, which is defined as the magnetic field B. Okay, I think I just don't want to write all of that out. It's cool? Okay, so let's like say. Okay, so we've now seen that the effect that the gauge fields that we had to introduce to impose local phase symmetry, the effect that those had on any measurable reality that we can observe was was the electric and magnetic fields. Or you could say, if you left it in this notation, you could just say it's this tensor, but it's nicer to see, especially if you're not super comfortable with this, that this ends up giving you electric and magnetic fields. Okay, so now I've said that that's a way that they could possibly depend on reality, right? Because now we've come up with quantities that are gauge invariant, but we don't have any way to measure them yet, right? The only way that we know how to measure things is by plopping a probe in something and then saying, oh, this has some effect, and reading that off. And we have no probe for this yet. the way that we would get a probe is, well, our only probe here is the wave function. It's matter. It's this thing that we know that exists. The wave function, we already know how to measure that. So we need to somehow couple these things, or we need to see how these things actually have an effect on the wave function. Right? Does anybody know how we're going to do that? There's one way that you couple the fields to matter. Or like, let's say the fields have an effect on matter. So, yes, actually, but that's a lot more complicated. We'll get to that next slide. It's very simple. This is like, I mean, it's charge. Yes, charge. And how does a field affect a charge? Like, what's the thing that a field can do to a charge? Right. So what's that called? For an electromagnetic field acting on a charge. There's a force. Right. So I'm saying we're gonna get the Lorentz force. That we need the Lorentz force in order to measure. Sorry, that was too pushy. But I mean, yeah, it's kind of it's a very like simple thing. It's not that complicated. But we actually, we have a way to do that. And the way that we get the Lorentz force is from, where is it? Where did I write it? Oh, from this guy. There is a little bit of vector calculus we have to do, so I'll reference that.
Measure how the field couples to charge by measuring how spin actually.
So yes, it could, but we don't have spin in this theory.
Okay.
Yeah, this is completely spinless. Spin is just like a complication. This is for, let's say, you could say a spin zero particle or spin zero field. But even with a spin zero field that has charge, that will couple to an electromagnetic field via the Lorentz force law. So we're going to derive the Lorentz force law, which just comes immediately from this thing.
Wait, just as a person who doesn't know a lot about like spin yet, what's a spin zero field that has charge?
I don't know if they exist in.
Like,
I don't think they don't exist in.
fundamental.
They don't. They do exist. They don't exist in particle physics, but they exist in this. Like I don't know if you heard of like Cooper pairs before. Like a Cooper pair is a spin zero. It's like two electrons in a pair, and they pair up and down, so they're spin zero.
That's like the thing that happens to the Pauli exclusion principle or whatever. Like,
Yeah. So yeah, it's like it becomes a boson, and like they exist, but we don't even need to worry about that here. Like this is. Spin is an extra complication you would add to this, but you could say that I'm doing single particle physics, and if I do single particle physics, then the spin doesn't actually matter for like that. It just like it's just another thing that kind of is an extra degree of freedom.
Okay.
Sorry. Yeah. Don't worry too much about like the spin. We won't even talk about here because spin is like it's funny. I'll say when spin, the way that spin actually couples. You can't like rigorously derive it, and even when you do, it's like a really long thing in quantum field theory called the spin statistics theorem. That like famously, people have tried to explain simply, and like nobody's ever been able to explain it without just doing like a long ass proof. So yeah, we're not gonna go there. When you do it in 115, you just sort of say that it exists, and then. But yeah, that's a good idea. Spin is important. It's just we're not there yet, or we won't be worrying about that. We need the Lorentz force law. So in order to do the Lorentz force law, all I actually need to do is just like take the gradient of this thing. So when I take the gradient of this thing, I want to say that there's a couple things that we can do. So first, I'll make some preliminaries, and actually, let me give myself more room for this, so you guys know what I'm. It's 11, 18, good. Okay. So the Lorentz force law says we want to take the gradient of this thing, which is basically a conservation of energy equation. So of course, when you take the gradient of an energy, you're going to get a force. So that should make sense. A couple things to note is that first, the gradient of epsilon, right, is equal to the gradient of minus h bar times the partial of theta with respect to t, which is equal to the gradient of, let's see, which is equal to, let's see, the time derivative of minus the time derivative of h bar gradient theta, which is p, right? And then using this definition, we can rewrite p as mv plus qa. So this is equal to minus the time derivative of mv plus qa. Right, is that clear? So I just substituted in for p because this defines p, right? You can just write it as that. Okay? And the reason why I don't leave it as p is because, well, that'll give us the right equation. Also, t is not gauge invariant, right? T changes under a gauge transformation, so it's not observable. So we don't want it in our final equation. The next thing that we have to consider is when we take the gradient of this thing, we're taking the gradient of the square of a vector field. There's, if you open up Griffiths, there's an identity that I'll just write. And that says that the gradient, I guess I won't write the identity, we can just say what it is. So the gradient of p minus qa quantity squared is going to be equal to, if you look in the notes I have, it's 2 times p minus qa quantity, not squared, crossed with the curl of p minus qa. I know this is going to get kind of cluttered. Right. Yeah. Oh, sorry. The notes is actually wrong here. There should be a minus sign. Sorry. But oh no. I know what happened. It'll work out. I will update these after the lecture. They see that I didn't write these correct. So this is p minus qa dotted with. Okay, I guess I'm out of the room. Dotted with a gradient, and then this is acting on p minus qa. Okay, and this is there. This is kind of long. So this is like a directional derivative acting on this vector field. And if you look, the notes, the correct one is the one with u squared. So it's 2 times u cross, like this thing crossed with the curl of it, plus this dotted with the gradient acting on this. We can make some simplifications here. The first simplification that's nice to do is that the curl of p is 0, because the curl of p is the curl of a gradient. So this is 0. Okay. Then I can rewrite both of these things. Right? This thing is mv, and this thing is mv. Right? And there is going to be like a 1/2m over there, but I'll pull it out. So, and then this thing is also mv. Okay. So if I write out what the equation is now, because that's the complicated parts, we can say the gradient of epsilon is minus the time derivative of, I guess we'll say minus m times the time derivative of the velocity, and then minus q times the time derivative of a. So that's just the gradient of epsilon from there. And then I have this thing, which I can rewrite nicely, is equal to 1/2m. So this 2 cancels, and then we have a 1/m. Times, this is mv crossed with minus qa, right? So minus qa. That's that. And then plus m squared, because there's 2 m's here. And then this is v dotted with nabla, or v dotted with del, acting on v, like that. And now I can rearrange it. So firstly, I can cancel these m's and the square. I'm going to remove, wait, my bad. There's one other thing I forgot to do, because remember there's a phi in this. So I should have written on this side minus q gradient phi. Sorry, not gradient. Great, yeah, great. So there was a minus, sorry, is that clear? I did that ad hoc.
So was the epsilon really supposed to be bar epsilon?
You are correct. Well, I guess I added it, I put it on this side, so I could put plus
okay.
Q phi on this
I see,
side,
yeah.
but I just, okay, let's maybe do that so it's consistent. This is plus Q bar phi, Q gradient bar phi, like that, because of the, and then plus, also, right, plus gradient V plus Q. Okay. Now, forces generally are going to be minus a gradient. So I'm going to multiply this whole thing by minus 1. So all of the minuses become pluses and all the pluses become minuses. I'll rewrite the equation here. And I can rearrange things. So notice that I have m v dot nabla v, and I have m, so m partial v partial t. So if I move this over to that side, this would become a minus, but then I multiply everything by minus 1, so they both become pluses. So on this side, I have m times partial v partial t plus v dot nabla v, which you should recognize from, or you might recognize at least from lecture 2, is this is the so-called material derivative, or the convective derivative, which was the derivative that we needed when we described the fluid, the force on a fluid, because the velocity field is varying. This is equal to, I multiply through by minus, so I have moved this over to this side, this becomes a plus on this side, then multiply by minus 1, so this just becomes a minus on this side. So then I have minus q times, I guess, plus q times partial a minus partial a partial t. And then we have minus q phi because this is multiplied by a minus. Right? Let's do, so you can kind of see how this is shaping up. And then on this side, we have v cross, oh sorry, this should be curl of minus qa, because there was a curl here, so it's curl of minus qa. So curl of minus qa, so then this is a minus becomes a plus because we multiply everything by minus 1. I guess this should just be phi. No, not phi, sorry, gradient phi is what I meant to write. Okay. We have curl of A, and the Q factors out because I'm pulling it out of this. So we have plus curl of A, and then plus these things, or minus these things, right? So it's minus gradient of V plus Q, right? And let me write this lower. So this is minus gradient of V plus Q. Okay, so this thing you should now recognize, right? This is the electric field. Oh my gosh, there should be a V cross this because there's a V cross that. Sorry, V cross curl of A. And this is V cross V. So this is a force, right? This is the Lorentz force, or it's, we won't say Lorentz force. It's a force. The force on our matter is equal to Q E times V cross B, and then minus this term. So in the limit of classical mechanics, which is two things. Remember, classical mechanics is the limit as h bar goes to 0. So in the classical limit, this would be 0. So Q is 0. We're going to ignore the external potential because that's like saying you're going to put your charges on a hill or something. That's like irrelevant. So this term is pretty much irrelevant. In the classical limit, this goes to 0, and this is like kind of not important. And in the limit, we have we can't say, quantum mechanics, you can't really say you have a point particle. You can say you have a very, very tightly peaked thing. Then your velocity field is basically constant in space, so this term is 0. And so you get m times partial v partial t is equal to q e times v cross v. which just is the Lorentz force law. And so this is how we can couple, this is how we could possibly measure the effect of the gauge invariant fields.
Can you talk here about how h bar goes to 0 in the classical limit?
Well, that was just a quick discussion last lecture. Remember, these equations are almost the same as the fluid equations. The only difference is this q, which is defined like this. So in the classical limit, we generally like to think of as h bar goes to 0, but it's here very clear why that's the classical limit, because as h bar goes to 0, q goes to 0. And in that limit, we recover exactly a classical equation. So does that make sense? Okay, yeah, it's just because that's what the classical limit is. And you can see that by saying that, we'll talk about this more next lecture, but interference is caused by q. And in the classical limit, we don't have like interference of particles. So in the classical limit, q goes to 0, so there's no interference. That's another way to think about it. Yeah.
I don't know if you said this already, but I think you mentioned last lecture we were going to discuss why psi doesn't it could be 0 and this still works.
That's going to be next lecture.
Oh,
yes.
Okay.
There's one. Yeah, that's a caveat, and that will be very important for this
Okay.
lecture. But we will talk. That makes the most. I won't say makes the most sense. That has the most important impact in the context of E&M, I think. So that's why that will be about half the lecture. I think will be dedicated to that.
That's why we're doing this first.
Yes.
Okay,
Yes.
yeah.
That's why we're yes, exactly. I also think I think it's nice to see how you do this. I don't know if you'll do. I don't know. You're in 115B, right? So in 115B, you kind of just say all of these things. Like you basically just say you have to do this, and they don't really tell you why. When that was part of the motivation for this class, is I kind of wanted to make it at least understandable why you would possibly do that. So we have at this point. I think. Does anybody want this for anything? Cool. At this point, let's see. Oh, it's 11:30. Yeah, I'll say so. I'm not going to complete everything in the lecture notes. You can read them if you want. It probably won't be super clear, but we haven't quite completed electromagnetism. There's a picture that maybe I should put in the notes. That's very, very cute, nice to draw, and that is to say, okay, what we've done so far in this course is we have sort of two different fundamental or measurable quantities that we care about. We either have the wave function, this is the Schrodinger, the wave function slash like the rho v, and then also epsilon, but I want to think about it as just rho v because you could determine epsilon, right? So these are like your matter. This is matter. Okay, it's what it is. It's like describes matter. Now, in this lecture, we've discussed a new quantity that is kind of separate from those, which is A and phi. So the gauge fields, and importantly, really it's just these, but importantly, they're gauge invariant manifestations, E and B. Okay, so these things are up until now separate. We previously had described how matter interacts with itself, and that was through, the ignoring this QA and this Q phi, that was through the Schrodinger/Madelung equations. So this interacts with itself through the Schrodinger equation / Madelung. And this is Madelung without gauge fields. Right? And this was completely decoupled. We just showed that this thing, these things, are able to influence matter, and so they are a measurable thing. And the way that we measure them is through the Lorentz force law. It could technically, you could say the Madelung equation with the gauge fields, but it's much easier to think about it in terms of the Lorentz force law. So these affect matter through the Lorentz force law. But we haven't filled in the remaining two sort of arrows, which is how these things affect themselves and how these are affected by matter. Okay? This bottom one you can mostly get, and that is because we have these things called the Bianchi identities, and these are we get these for free. And that is just to say that, well, we know that So the way that these would affect themselves and the way that matter would affect them is going to be determined by Maxwell's equations. That's the thing that we need to fully complete E&M, right? We need electric and magnetic fields and potentials. We need the Lorentz force law, and the last thing we need is Maxwell's equations. We get 2 of those for free because the curl of the electric field is the curl of, or sorry, not the curl. What's going on? Oh yeah. Is the curl of minus partial A, partial T, plus minus gradient Phi, which is equal to this kills the gradient. And it's the curl of the time derivative, but you can swap those. So it's minus partial B, partial T. So that's one of Maxwell's equations that you might recognize. And then the other one is even simpler. It's just that the divergence of the magnetic field is equal to the divergence of a curl, which from vector calc you should know is 0. So you have 2 of these. So you can say these are Bianchi. And we haven't actually completed these because we should really have another thing that says like the curl of B is related to the time derivative of E, right? The problem is really though that we don't have this relating to that, like how this affects this, and in fact, if we figure out how this affects it, it'll turn out that we can sort of complete this picture. I really thought about this for a long time about how to approach this. The problem is you can't quite complete this picture unless you use some kind of not advanced, but Lagrangian mechanics that you aren't super familiar with. So I've included those in the notes, and we have time, so I'm happy to go over them. But just know that in order for me to talk about these, it's going to be significantly more advanced and probably much harder to understand what I'm doing if you haven't seen Lagrangian mechanics before. If you have, it's going to probably be okay. So yeah, you guys feel free to like leave town if you want. I mean, you don't have to, but like if you haven't seen this, I totally understand, and don't feel bad about not understanding what I'm about to say because it will be more. Cool. Okay. Yeah, if everybody wants to say, you can. If not, I'll are there any questions about what I've said so far?
Do you mean like 115C?
No, 104 is the only thing. Just literally, I'm going to write down the Lagrangian, and in order to motivate that Lagrangian, and also to get the equations of motion from it, we need the Euler-Lagrange equations. Which have you heard of?
I think I could get by with just 32, right?
Probably. Yeah. There's going to be some extra stuff, but yeah, I don't want to. Yeah, I mean, I marketed this course as just needing 150A, so this is a caveat that
Also about library. In the 115 series, even in 215 series, maybe we are using 120. But for the quantum field, we are instead of 120, we are using 1. Could you elaborate the reason we are going to use Lagrangian for like quantum field and for the quantum phase?
So I'm not using the Lagrangian for the quantum phase here. It has nothing to do with what I'm saying. We're not doing quantum field theory because we're not quantizing the fields. The fields here are entirely classical because they exist and they are continuous.
It's just very cheap for them.
No, I like noting it down. So I'll give you like I should.
So the Lagrangian, so the Lagrangian will be used for to derive the grid of motion.
Yeah, you could do that, but I'm not. Like, if you want to do if you want to do a quantum Lagrangian, you have to do path integrals, right? So we're not going to do path integrals because I don't want to do quantum field. The whole point of this is just to not do anything like this. So, okay. If everybody, I don't know, I guess, but everybody that wants to stay, I'll now do this. It'll take probably the remainder of this time. But if you have any questions about this, you should ask them now so that I don't let them.
You mentioned repairs.
Yeah,
Here somewhere, and I was like, like elaborate on that.
So yeah, Kareem asked about spin because he was saying I was not super familiar with spin. He was asking this in response to me saying that this is a spin zero field. Right? Spin zero field means that psi itself, the wave function, doesn't have spin. I never said that it has anything like spin. And when not having spin is the same thing as having spin equals 0. Cooper pairs are,
I have a lot of random
draw it. A Cooper pair is very heuristically a pair of electrons that has spin up and spin down, and it has momentum p and momentum minus p. Okay, when you pair these, they have net spin 0. So this is just an example I gave of, as you know, probably a superconductor. It's a field of particles. You have to quantize it. So it's a quantum field of particles that has spin 0. So there is actually a case of a, and they also have charge. Like this is charge 2.
Yeah.
So it's a charged spin 0 field.
Charged in 0 fields. Okay.
Yeah. The others, I don't think, like the Higgs boson doesn't have charge. But there's a cool relation here that I was debating. Like I'll say, yeah, I can go to 1140 to talk about this, so I have a bit of time. There were two directions I could have gone with this course. One of the directions was doing what I'm doing, which is kind of doing like topological phases, that type of thing. The other direction that I could have gone post basically the next lecture was to talk about superconductivity, and that is the reason why I didn't, and that would have talked about this and how this is kind of related to actually the Higgs field in particle physics. It's a really cool topic. The main reason why I didn't do that is because there's like two reasons. One, the physics is a lot more advanced for like a lot of things, and I don't think I could do it in a way that is kind of like this, where I'm sort of going slower and making sure everybody understands. And also because there's one point where you literally have to just suppose that something exists, and it's a very non-trivial thing. It's basically you write out this random free energy that you then derive everything from. So I didn't want to do that because it's kind of, you know.
Yeah.
But yeah, that's, so I don't know, does that answer your question?
Yeah, no, it doesn't. Yeah. I heard Cooper pairs and I was like, pro tip like a dog.
Yeah. Okay.
Cool.
Yeah, thanks for coming out. Yeah. All right. I think 10 minutes should be fine. So the only thing that I need to do, let's see, this is a bit hard. I don't really want to erase these. I think I can erase these because you guys kind of, I don't think this.
On the left side.
Huh?
You have space on the left side.
Oh, do I?
Also, your phone is on low battery.
That's all right. Oh shoot, please tell me it didn't stop recording. It did not, thank God, okay. I have some space, but I kind of want to keep this in the center. All right, I'm gonna erase this. I don't think I need the transformations at all because I already used those. So, did I define? No, I need these. Okay, I'm gonna erase this side then, because this is more like not as important. The only thing, I'll write down the new stuff if I need to. Okay. Yeah, it's kind of, when I asked Matthew about what I could do better last lecture, he said board space, which admittedly was true, but I also want to record everything, so you have to compromise at some point. Okay, so, yeah, I'll go kind of fast. So, okay, if you want to try to determine these things, you have to write down a Lagrangian. The Lagrangian is basically just going to be the, it's going to be determined very easily from our energy. So if you want to write down sort of the Lagrangian from the matter, it's pretty simple to do that. Because I guess I already need the equation back, but remember, I lost my thing. We wrote previously that epsilon is equal to p minus qa, quantity squared over 2m, plus q phi, and then plus some other stuff that's unimportant. This is an energy field. If we want to find the energy density, we would just multiply this by rho, because rho would give us, it's like the density times like the field is going to give us the density. And we could try to write down a Lagrangian from that, because basically this is a kinetic term and this is a potential term. And when you write down a Lagrangian, you just flip the sign on this term. You just flip the sign on the potential energy. There's a more rigorous way to do that I don't have time to say, but what you would do is you would like actually figure out what the conjugate momentum are and do the Legendre transform. But effectively the Lagrangian for the matter is going to be equal to P minus QA squared over 2m, and then just minus Q phi plus da da da. And if we try to then apply Euler-Lagrange to this, we can write, right, so partial Lagrangian matter, partial either A or phi, because these are sort of, we basically want to see how this varies with respect to these things. Say partial phi is a little easier, minus the, so because this is a field, it depends on space and time. So it's not going to be the time derivative of the partial of the Lagrangian with respect to q dot. It's going to be the derivative with respect to all 4 spatial coordinates. Because now these are things that are fields that are defined at every point in space and time. So it's going to be, for phi, what it ends up simplifying to is the divergence. So this is like the partial with respect to time, but it's now with respect to space, of the partial of Lagrangian matter with respect to the gradient of phi. So it's like basically varying with respect to the E field. And this is equal to 0. But the problem is there is nothing in this, so this is 0. And this, right, is equal to just minus q. So you get minus q equals 0, which says that q equals 0, which is like what happened, right? And the problem that happened here is we basically literally the problem is exactly that this thing is 0. We assume that there is no energy associated with the fields. We didn't assume that there is some self-energy associated with the fields that we just didn't take into account, and so that made this go to 0. And that means that we should say that there is no charge, which is kind of like, well, that just defeats the point, right? It says the q is 0, so all of this is 0, and we just get back the previous theory. In order to do that, that means that the Lagrangian for the matter fields is not the full Lagrangian. We need to figure out what the Lagrangian is that also includes the energy associated with the fields. You might know that the energy associated, I guess, sorry, this should be multiplied by rho. So this should say rho q, but then rho is non-zero, so q is 0. So we need to find out what the energy associated with the field is. You might remember that that's like epsilon over 2 e squared plus 1 over 2 mu naught b squared. I'm not just going to cite that because that would be kind of unsatisfying. Though you could kind of think about it like that. The reason why that we don't have that immediately from our theory is because in order to actually get the field Lagrangian, we have to use the fact that electricity and magnetism is a Lorentz invariant theory. Notice we haven't done anything with Lorentz invariance at all, but you might know that, from 1 and 3, from 1 and 10, that E and M is inherently Lorentz invariant. And we've never used that, but it must be the case. And so that's sort of the missing piece that we would need to impose. So we need to figure out a Lorentz invariant quantity. The Lorentz invariant quantity that has to deal with the fields, we know that the fields are all encoded in F mu nu, right? So we need to basically create a Lorentz invariant quantity out of F mu nu, and the simplest one to do there is just F mu nu. F mu nu. This is clearly a Lorentz scalar just by I don't know. I mean, if you haven't taken 1 of 3, then it won't make sense. But I mean, this is, you can track the indices and so it doesn't transform. So that is what it is. And then for units, what we'll say is that in SI units, this becomes expressed in terms of the fields, epsilon naught e squared over 2 minus 1 over 2 mu naught b squared. So this looks like the energy density, but with a minus sign. Yeah.
Here, raising does matter because we're doing.
It doesn't really matter, but since I'm now actually citing special relativity, I'm gonna be more formal about it.
Okay. You're just saying that's a scalar, so it's.
Yeah, it's a scalar. So my point is we need a Lorentz scalar because we want the equation of motion, which this is going to give us an equation of motion. It needs to only consider Lorentz scalar quantities because otherwise then it would not be a Lorentz scalar, and so our equation of motion would be different. Which the whole, a big thing about ENM is that it is Lorentz invariant. So that says that this thing is the field Lagrangian. This is L field. And then we have that, so we say that Lagrangian, the total Lagrangian is going to be equal to L matter or let's say L field plus L matter. So now we have this extra piece, and we can now think about, what happens when you do this equation, right? So when you do this equation, now you're going to vary with respect to this. So this is minus grad phi. So this is the same thing as doing partial E and then putting a plus sign there, because E is, sorry, that's not correct. I don't know why I said that, that's just wrong. Let me not do that. Partial gradient phi, and let me reference so I don't mess up all my time. In order to do this, you would find that this thing is going to give me rho q, right? Yes, so I get rho q minus the divergence of this thing, which I can write as the partial with respect to the gradient of phi of, this is epsilon naught over 2 times gradient phi minus grad phi minus partial A partial T squared plus what is 1 over 2 mu naught B squared, because B doesn't include phi at all, so I won't even include that. The only thing that matters here is this. This becomes rho q minus divergence of, this is, I think, what is it going to be? Minus divergence of what is this? Gradient phi, right? Yeah. This is minus divergence of minus gradient phi times epsilon naught. Yeah. Minus epsilon naught gradient phi. No, sorry. Yeah. Minus epsilon naught times minus gradient phi times, what am I doing? Yes, this is what it will be. Like this. Yes. I think this one, yes. Sorry, I was doing the math fast. Equals 0. So this is epsilon naught E, right? And so this gives me that divergence of E equals Q rho over epsilon naught. So we identified this as charge density, which makes sense. And this is Gauss's law. Okay. And then because we're out of time, unless people want to stay, you could do exactly the same thing for the Ampere Maxwell law. So this is going to give me Gauss's law. It's in the notes, but basically you would do exactly the same thing, except that for the vector field, it looks like partial Lagrangian. I guess this should not be matter anymore, right? The whole Lagrangian, partial of the Lagrangian with respect to A minus the curl of the partial of the Lagrangian with respect to the curl of A equals 0. This would give you the Ampere-Maxwell law, which would be that the curl of B equals mu naught times Q times rho V plus epsilon naught partial E partial T. And you can identify that this is clearly the current density. So this recovers the Ampere-Maxwell law. So yeah, I didn't have enough time to go over that, but then this completes electricity and magnetism, because you also have Maxwell's rules.
Is that supposed to be squared?
Yeah.
It's not, right?
What is
The derivative would bring down the 2.
It wouldn't be. Yeah, you're right, because the 2 got sorry.
Yeah.
That's right. Okay. This should be minus.
That's still correct, yeah.
There you go. Okay. So I don't know if that helped at all. But I needed to, I put this in the notes because it's really like, it would hurt me to not finish Maxwell's equations, but it's like, yeah, unfortunately you kind of just have to do this. I really thought about it for a while and I don't know of a way to get to the last two things without doing this type of thing. Yeah, and then the notes are a bit more in depth about this. Yeah, just a little bit.
So people, I mean, I don't know, I've never taken like 110 or a class where they do this, but.
Well, they don't do that. They definitely don't do it.
Oh.
They definitely do
What
that.
class does this? Like,
Probably 225? Probably 225, yeah. Same thing. I'm gonna save my battery now.